We're going to take a look at introductory statistics and the normal distribution. So when we talk about the normal distribution, this is a continuous distribution of information, and it's the most important one because it's what we use widely, and yet it's also widely abused. The way this looks is what we call a bell shape. It's a nice hill that has a nice even slope. And we see it happen a lot of times when things are standardized and in many different disciplines. So an example of this is if you ask enough people about their shoe size, you're going to find that your graph data is going to create this normal distribution. And the more people you ask, the more closely your curve is going to look like this. So the normal distribution has two parameters, the mean and the standard deviation. So when we talk about the normal curve, we use those two things to discuss it. And we write the mean using the mu, and we write the standard deviation using the lowercase omega. When we're looking at this function, it's telling us the probability that somebody is going to fall into a certain region of this graph, of this hill. So we will be using some different numbers to calculate this. The formula that's in the lower left-hand side is not something you will calculate. You will either use the table or technology to find it, but it's just important to mention that this is used to find how likely a certain value is to be included. In the normal distribution, the slope is nice and symmetric, and it doesn't always come out exactly symmetric, but it's close to it. And what happens is the mean then is the highest point because that's where the data is going to stack up. So we call this the standard normal distribution, and that's just another term that we use. Here's a little history. This was developed by de Moivre as an approximation of a different type of distribution. His paper wasn't discovered until much later, and then we have some kind of different claims here to fame, and we didn't have the internet or things like that at this time. So it's very tricky to really come up with who really did things first, and sometimes certain people are credited to have doing things first, and then we step back and we change. And so sometimes in your textbooks, you'll see a little bit of different context because the people who wrote the papers, some took it further than others. So it's really hard to say this person found every aspect of this concept before the next person. In our standard normal distribution, we have things called a Z-score. So a lot of the times we don't ask millions of people or thousands of people a question. So we have to convert the distribution that we have into a normal distribution so that we can then do some calculations. So the Z-score is when you take the value that's given to you by the person or the survey, you subtract the mean from it, and then you divide by the standard deviation. That's going to give you the Z-score. So if I'm given a curve like this, the mean for the standard normal distribution here is 0, because 0 is the highest point. The standard deviation is going to be 1, and so that we can find our Z-scores using that basic information if this was our curve. So here's an example. What is the Z-score of x if x is 1 and I have my normal distribution with a mean of 12 and a standard deviation of 3? So you're going to plug that into the formula and do 1 minus 12 divided by 3, which is negative 3.67. That is our Z-score that we're going to build on later even more. Here I have another example where we have a real-world problem with a mean of 5 and a standard deviation of 2. Now it tells us that the Z-score is 2.5 when x is 10 pounds. So using that information, I can work backwards and set 2.5 equal to my x value minus the mean of 5 divided by the standard deviation of 2 to work this backwards and find out if what I have is correct. In part B of this question, I'm looking at gaining 3 pounds and a negative weight loss. This is going to mean that my Z-score is going to be related to the value of x equals negative 3, and it's going to be so many standard deviations away from it. So it's going to be 4 standard deviations to the left, because when I find my Z-score for using the x value, it's negative 4, which means 4 away from the mean. So the Z-score is going to correlate to the distribution and tell you exactly how far it is from the mean. The empirical rule is just a statement that 68% of the values fall between this region, which should make sense. It's the highest region. So the bulk of people fall somewhere in there. And then 95% of people are going to fall from here to here. And 99.7 are going to fall from those two. So really it's just a common sense statement of how likely it is that someone's going to have a shoe size between this value and this value, if we're continuing on with that shoe explanation. The empirical rule is also known as the 68, 95, 99.7 rule because it just kind of explicitly states what I just said. Another example is given here with an X that has a normal distribution, a mean of 50, and a standard deviation of 6. So my mean is 50, so this is 56, this is 44. Because I'm going to add my standard deviation here, I'm going to subtract my standard deviation from here. So 68% of the values lie between 44 and 56. I can continue this and look at that second standard deviation. So if this is 50, I would have 56, then I would have 62. And then I would have 50, 44, and then I would take away and have 38. So 95% of people are going to fall between 38 and 62. And then I can take that a step further to find the third standard deviation. So I can find the actual value given the mean and the standard deviations. I can find the X values that people are going to fall within that range from. And that is the end of the normal distribution. So we're going to look at Z-scores, the empirical rule, and we're revisiting the mean and the standard deviation.